Hi, the topic of today's lecture is on equivalence of norms. In functional analysis, equivalence of norm is a basic concept. It plays a very important role. The idea is on a given vector space over course RC, there may exist two different norms. Okay, and for functional analysis purpose, it does not matter. They may look different, but in some sense they are equivalent. Okay, and textbooks and most often authors prefer define the notion of equivalence of norms in terms of chain of inequalities and work with that. And that's very natural because functional analysis is analysis. So sometime or other I have to keep estimating, right? So it's a very natural. Okay, I should learn the definition. That's a one which is most useful too, no doubt about that. But one should understand how those chain of inequalities came about, why we used it as a notion of equivalence. The purpose of this, the goal of this lecture is to explain that. Okay, let's get started. Yeah, this is the title of the lecture, and the basic reference is a book written by me and Sukumar, Functional Analysis, and my YouTube channel is given here. Right. So let us get started. So as in functional analysis, we will let X denote a vector space. Okay, and over a field K, the field K may be R or C. Okay, we don't really require that. Okay, so I hope all of you know the definition of a norm. Okay, that's a map from X to R satisfying some properties. Okay, I hope I don't know to say that. Okay, but what is more important is, yeah, just 1 second. Yeah, okay. So one of the most important thing you may know is the so-called triangle inequality. This is true for all x and y in X, right? And of course, as usual, norm of x is greater than or equal to 0 for all x, and equality holds if and only if x is 0. And the third thing is, for any scalar lambda in the field, lambda x will be equal to mod lambda times norm x. I hope I remembered all the properties, but anyway, right? Very good. So once I have a norm, I have a metric on x cross x to R. Okay, how do I define d of xy equal to norm of x minus y? Okay, using various properties, you can show that this is d is a metric on x. Okay, once I have a metric, I have topology. Right, and this topology also we call the topology on x induced. Okay, topology on x. Okay, the norm topology I will also call the norm topology, where the, okay, because d came from the norm, therefore I will also call the topology as the norm topology. Is that point clear? Right, now comes a problem. Suppose I have a vector space over the field K, and suppose I have two different norms on x, right? So I want to say these two norms on x are the same, are equivalent. Okay, not same, I am going to say is equivalent to, or simply say these are equivalent equivalent if the topologies tau I induced by the norm I, okay, I equal to 1 to 2 are the same. You understand? Tau 1 equal to tau 2. This is the topology induced by the first norm. This is the topology induced by the second norm. So I say they are equivalent. Okay. Is the definition clear? So this is my definition. Given two norms on a vector space, I say they are equivalent if the topologies induced by these norms are the same. Okay, the norm may look different. You may recall on Rn, if I have this usual Euclidean norm or this max norm or the summation norm, okay, they are the same. This is maximum mod xi or zi, okay, this is summation mod xi, and this of course mod xi squared and to the power half. Okay, these are all equivalent, that you might have seen. Okay, but anyway, there will be another video where we look at various norms and check whether they are equivalent or not. Okay, that will be a separate issue, so I don't want to be distracted. Is this definition clear? Yeah. So pause, review, proceed. So if you already know some other definition, okay, hold it for a minute, we will arrive at it. So this gives the real reason why we are going to get equivalent norm. Okay, why we have to study the equivalent norm, because the topologies are the same, therefore continuity etc. all topological notion will be the same. A set will be closed with respect to the first norm if only it is closed with respect to the second norm, because the topologies are the same. You understand? These are the reasons why we want to study equivalent subnorms. Now it gives a reason. You see that? The moment we put it this way, we know that. And similarly, if I have K, a compact subset of with respect of X norm 1, if only it is a compact subset with respect to second norm. Why? Because the topologies are the same. Now do you understand the reason why we want to look at it? Very good. Okay. So let us get along. So the whole thing depends upon the following fact from topology. Suppose X is now just a set, not necessarily a vector space. Right? Suppose I have two topologies, tau 1 on tau 2 on X. Right? Then tau 1 equal to tau 2 if and only if you look at the identity map from X tau 1 to X tau 2, this is a homeomorphism. Of course, you can also change it to X tau 2 to X tau 1 also. Okay. So this is the first fact from topology. Let's quickly go through that. Yeah. Suppose I start with a V in tau 2. Right. Now let's assume first notice that if tau 1 equal to tau 2, the identity map is a homeomorphism. Therefore that's clear. Right. So this portion is clear. Tau 1 equal to tau 2 implies identity is a homeomorphism. Identity where, remember, I have to specify which topology is a homeomorphism. When I write simply identity, that's not good enough. I have to say identity from X tau 1 to X tau 2 is a homeomorphism. Okay. Now let's assume identity from X tau 1 to X tau 2 is a homeomorphism. So I want to know whether tau 1 equal to tau 2. Yeah. So since this is a first, remember this identity is homeomorphism, therefore this identity from X tau 1 to X tau 2 is continuous. Right? Therefore let us take V in tau 2. Then what is the inverse image of this? This is V itself. Right? X belong to this if only identity of X belong to V. Identity of X is X belong to V. Therefore these two sets are the same. Do you understand that? Okay, remember this is my favorite mantra. X belong to F inverse of V if and only if fx belong to B. This is the only way to work with inverse images. Okay, x belongs to identity inverse of B if only if identity of x belongs to B. That means x belongs to B if only if, okay, it belongs to identity inverse of B. Finished, right? Therefore, since identity map is continuous, therefore this must be in tau 1. Do you follow that? So what does it show? I start with any v in tau 2, then I show tau v is in tau 1. Right? Now how do I prove the other way around? Therefore that shows tau 2 is contained in tau 1. How do I show tau 1 is contained in tau 2? Yes, you will look at identity map from x tau 2 to x tau 1. Okay, use the continuity control or interchange tau 1 and tau 2. Yeah. So pause, review, proceed. So what I have shown? I have shown that given a set, two topologies tau 1 and tau 2 are equivalent are the same if and only if the identity map from x tau 1 to x tau 2 is a homeomorphism. This you must have learned in topology, and if you have watched my topology lecture, again you would have learned. Anyway, I have given a complete proof now. Right? So, right now let's look at, so I have this now is a vector space, okay, over K, and I have two norms on that, right? I want to say they are equivalent. That means the topology is tau 1 equal to tau 2, right? Yeah, so let's assume they are equivalent, right? That means tau 1 equal to tau 2. This, but then this happens if and only if identity map from x of norm 1 to x with the norm linear space this is a homeomorphism. Right? That's how we seen. So we in particular identity map from x norm 1 to x norm 2 is continuous, right? Correct? And in fact we are going to use only continuity of this map only at 0. Okay, so this has nothing to do with identity map. Okay, remember, since x is a vector space, identity maps a linear map from the vector space x underlying vector space x to the underlying vector space on the codomain. They are the same, there is no difference. You follow that? Yeah. So we have to understand the continuity of linear maps between two non-linear spaces. Okay, so we will take a digression. So let x, okay, be on this, and y. Now I am not going to write as a lot of teachers write y, x, etc. The context should make clear which norm I am talking about, whether it's a norm on x or norm of y. So suppose T is a linear map from x, this norm linear space, to this norm linear space. Okay, right? Assume T is continuous at 0. That's it, right? Let's go through the definition. Since it's continuous at 0, what do I know? Let us recall. I want to use epsilon delta definition of continuity because we are in a norm and it's a metric space, right? So if I have a function from x to y, metric space is with metric D, right? So I want to check its continuity at x naught. What do I do? Look at f x naught, okay, and look at an epsilon, right? Therefore I have call it as if you want y naught, be y naught of epsilon. Then I want to say there exists a delta positive so that bx naught of delta I can form for every x here, fx belong to this. That is, given an epsilon, there is a delta, so that distance between x and x naught less than delta implies distance between fx and fx naught is less than epsilon, right? You follow that? So I want to use a continuity. Therefore, what is my point here? My point x naught is 0. And what is fx naught? Here is t of 0. Now what is t? T is linear, therefore z of 0 is 0. Do you understand? Right? Now for every epsilon I should be able to find a delta. So let us choose epsilon equal to 1. Right? Now what do we know? Since t is continuous at 0, there is a delta positive, so that the distance between x and 0 is less than delta. That means this is same as norm of x is less than delta, implies the distance between tx and t0, this is nothing other than distance between tx and 0, but this is nothing other than norm of tx should be less than 1. That is my epsilon. Now notice that I am using the same notation, but all of you are smart, right? We are all intelligent. This x belongs to capital X, therefore norm, this norm means norm on x. Here tx belongs to y, therefore norm of tx must mean y. So why should I keep writing this and taking time? Yeah, that's what I mean. Okay, is that clear? So there is the delta. Let me rewrite it again. There is a delta, so that norm of x less than delta should imply norm of tx is less than 1. Right? This is by continuity. They are using just continuity of t at 0, and the fact t is a linear map. Right? Where did I use the t is a linear map? Because this is norm of tx minus 0. Right? Okay. In fact, if you notice, I didn't even use linearity, I use only additivity. Okay, let's not get worried about. Okay, this tx minus 0, this will be norm of tx minus 0. Alright? Okay. Do all of you understand this? No problem? Okay, that's good. Now you give me any vector z, okay, non-zero vector in x. Okay, then let us look at x defined by delta by 2 by z by norm z. Okay, this is a vector in x. What is its norm? Its norm is delta by 2, because delta by 2 and norm z will come out, delta by 2 1 by norm z will come out, and then I will write norm z. Right? Therefore the norm is this, which is less than delta. Right? Therefore what do I know? Norm of tx is less than 1. Right? But now t is linear. Right? Therefore t delta by 2, let me write delta by 2 to norm z into z. Yeah, x is this. Right? Now this is a scalar, t is linear, that comes out. Therefore this is delta by 2 norm z. This is 2, this is norm z into t of z. Yeah? But now delta by 2 by norm z, this is a positive number. Right? And this is a norm by norm property, this is delta 2 norm z into norm of tz. Right? This is less than 1. So what does this imply? This implies norm of tz is less than 2 by delta times norm z. Okay, this is for which z? For every z which is non-zero in x. Yeah, and suppose z is 0. Right? Is this obvious? So now z is 0, this will be 0, t of 0 will be 0, this will be 0, therefore 0 less than 0 will be wrong. So what do? I change it like that, less than or equal to. Do you understand the trick? So what do you think I have proved? Let me summarize. If T is a linear map from X norm, the norm linear space X to norm linear space Y, and is a linear and continuous at 0 in X, implies there exists a constant C, so that for all X in X, norm of Tx is less than or equal to C times norm of X. In our case, this is 2 by delta. Yeah. Do all of you understand this? Yeah. Right. So just using continuity of the linear map at 0, I got it. But this actually shows the other way around. Okay. Now we claim continuity of t at 0 implies continuity of t everywhere on x. That's very easy. Suppose I want to prove continuous. Okay. Continuity at x in x. What does it mean? Again, go through those. Use the epsilon delta definition. We will do that. Right. So start with any y. This is any x dash. Okay. X. Start with x dash. Then I have to estimate norm of tx minus tx dash. Distance between tx dash. Right. But remember, this is because t is a linear, in fact additive, it is t of x minus x dash. This is equality. But then remember, it is already continuous at 0, therefore I know there is a constant c, so that this happens. Right? Therefore, what do I get? I get this is less than or equal to c times norm of x minus x dash. Alright? This is c times distance between x and x dash. Right? I am sure all of you must have seen, if I have metric space X, I say F is a Lipschitz. If there exists a positive constant L, so that distance between fx1 and fx2 is less than or equal to L times distance between x1 and x2. Okay? And any Lipschitz function is uniformly continuous. Why? If you give me an epsilon, okay, I want this to be less than epsilon, so it's enough if I make this less than epsilon, therefore I have to only choose delta to be epsilon by L. Okay, with this delta I get Lipschitz. Alright, so let's go back. So what I have shown, if t is continuous at 0, I proved that there exists a constant c, so that for all x norm of tx is less than or equal to cx. Okay, after that I proved t is continuous at 0 implies t is actually Lipschitz continuous on x, and hence it's uniformly continuous and continuous on x. Okay, pause, review, proceed. Now let's go back to our original question. So I have x and I have two norms, and I say they are equivalent. Right? Okay. Right. What does that mean? The topology is tau 1 equal to tau 2. Right? But if the topology is, so tau 1 and tau 2 are two topologies on the same set X, they are equal. That means the identity map from tau 1 to x tau 2 is a homeomorphism. So in particular, the identity map from the norm linear space to this norm linear space is continuous, and in particular continuous at 0. Yeah, right. Remember, identity map is a linear map because X has a vector space structure, right? Therefore, what do I know? By just now whatever I said, there exists a constant C2, so that for all x and x, okay, identity of x with respect to the norm here is less than or equal to constant times with respect to the norm here, right? Remember T of x in the domain space. Okay, this is norm is the codomain space, this is the norm in the domain space. Therefore what do I have? Therefore this one, but this is nothing other than x1, right? Have you understood that? Right. Now I can interchange 1 and 2. What will I do? Now I look at identity map from x with respect to the first second norm to x with respect to the first norm, and this is also continuous at 0. Why it's continuous at 0? Remember, identity map is a homeomorphism. Therefore the inverse map, what is the inverse of identity map? It's itself. Therefore inverse of identity is a map which is identity, which is x from norm 2 to x with norm 1. Okay, so this is also continuous at 0. Do you understand? Therefore again there exists a constant c1, so that for all x in x where in this space, okay, what do I have? Look at identity of x where in this space. Therefore what norm I have to take? Norm here I have to take. That's less than or equal to c times norm here, but this says nothing other than c1 times. Therefore this says norm of x1 is less than or equal to c1 times norm, second norm of x. So this is for every x. Right? So let's look at two things. So I have got these two things. Okay, so let me just write it. So I have shown that norm of first norm of x is less than or equal to c1 times second norm of 2. That in turn, okay, and second norm of x is less than or equal to c2 times norm of first norm of x. Right? So this I can rewrite as, remember c1 is positive, therefore I can write it as 1 by c1 times norm of x. First norm is less than or equal to second norm of x, but second norm of x is less than or equal to c2 times first norm of 1. So call this as b, call this as a. Then what do you have shown? If these two norms are equivalent, then there exists constant a and b positive, so that a times the first norm of x is less than or equal to second norm of x, which is less than or equal to first norm of b times first norm of x. This is what you have proved. Yeah. So what have we shown now? If the two norms are equivalent, we have shown this chain of inequalities. Okay. Implies this. Right? That's what I wrote in anyway. Yeah. Okay. Now conversely, let these be norms on x, so that there exists positive constant a and b, so that a times first norm is less than or equal to. Then I want to show the norms are equivalent. What does that mean? That is, the topology star 1 induced by norm 1 is equal to the topology tau 2 induced by norm 2. But that happens if and only if the identity map from x tau 1, x tau 2 is a homeomorphism. right? So to check this homeomorphism, it's enough to check identity map from x tau 1 to x tau 2 is continuous, and identity map, because the inverse of that is continuous. So enough to show this. Yeah. So pause, review, proceed. Now that's very easy. Why? Because if you go back to the thing, what did I do? I said T is a linear map from non-linear space. Okay, linear. Then T is continuous at 0. Okay, implies there is a constant C, so that norm of Tx is less than or equal to C times norm of x. Yeah. Then we proved that it is implies T is already continuous on all of x. Alright. On the other hand, suppose T is a linear map with this property. Okay. Then I claim T is continuous. This proof is what just now we had already shown that. Right? This we already saw. Do you remember? Therefore, now let's look at. I'm just recalling, just because I did it, you might have forgotten. Okay, don't get confused. Alright, now start with any x in capital X. What do I know? Norm of identity of x in the codomain. Okay, now I know norm of x2 is less than or equal to C2 times norm of x1. So what does this show? This shows that identity, okay, from x first norm to x with second norm is continuous, right? And similarly I will have the second one, identity from x second norm to identity with the first norm. Okay, so start with any x in x, then identity of x with respect to the first norm is what I have to look at, but that's like is same as norm of first norm of x. Now what do I know about first norm of x? I know that a times first norm of x, okay, is less than or equal to norm of x second norm of x, that is first norm of x, yeah, this is equal to is less than or equal to 1 by a times second norm of x. Okay, this is your some constant, right? Therefore identity map from this space to this space, x with the second norm to x with the first norm, is also continuous. Therefore I have proved, okay, these two norms on x are equivalent. That means the topologies induced by these two norms are the same if and only if there exist constants a and b, so that a times norm of x is less than or equal to second norm of x, that's less than or equal to b times first norm of x. So we have proved that result. Okay, most often this what we proved as a theorem, this is usually used as a definition in textbooks, most often, not always. For example, our book is an exception. So I hope you understood why the equivalence of norm is defined, and also it gave you some kind of an idea about how to work with the linear maps, continuity of linear maps between non-linear space, etc. on the way. Okay, I just wanted to make it as self-contained as possible so that you enjoy the course. And please remember what I keep saying, whenever you go through something, if it uses some simple facts which you have seen earlier, don't assume, yeah, I have seen it. No. What you should do is stop for a second, few seconds, and quickly see how you proved it. You may not get the complete detailed proof, but you get the basic ideas. Slowly you will see that's more than enough for you. Okay, you don't have to memorize the proofs. Your brain would have been, all the proper connections will be made, therefore the signals will travel much faster, and there you will get a complete proof also soon. This is a trick which I learned. I hope you also do and improve upon that. Okay, right? Younger generation should always be better than the earlier generation. Okay, that's how human race progressed. I hope you'll do it. Okay, we'll meet again. Bye.